will be discussing the type 2 variable sampling plans. As I have already stated, there are the two types of variable sampling plans, and the first type already we have discussed. Now we are going to discuss the variable sampling plans used for controlling lot proportion non-conforming. And obviously, I will be dealing with several a number of numerical exercises. Is it okay? So now these plans are used when controlling of lot proportion non-conforming is of concern and needed. So this point already we have elaborated. Okay. Not only the process average you need to control, you also need to control the proportion non-conforming, and this the proportion non-conforming, you are it's not that it is related to the attributes data. Many a time whenever we say the proportion non-conforming, we may assume that it is related to the attributes data. So you may also in the defined proportion non-conforming with respect to a quality characteristics for which the variables data are collected. That means the exact the deviation from the standard or from the nominal value, if any, you can determine, and accordingly you can determine this proportion proportion non-conforming related to a particular lot. So given the quality characteristic for which the sample values are obtained, the proportion non-conforming can be estimated. Is it okay? So you must not have any confusion on this. Now, so let us talk about the variable sampling plan for controlling lot proportion non-conforming when the quality characteristic is of single specification limit type. So for a single specification limit type quality characteristic, there are many such quality characteristics you come across. Now it is assumed that that this quality characteristic is normally distributed with standard deviation known, right? Like in previous cases we have assumed. The proportion non-conforming can be computed with the procedure as follows. Is it okay? So when the normality assumption holds, proportion non-conforming you can calculate. So how do you calculate? I'll just explain one procedure. Suppose it's a lower specification limit type quality characteristic. So what do you do? And this the lower specification limit is specified as capital L. So you compute ZL. Is it okay? So what is ZL? Actually the standard normal deviate. Is it okay? So ZL is equals to x bar minus L by sigma. Now what is this x bar? X bar is the sample average and capital L is the lower specification limit. And what is sigma? Sigma is the process standard deviation which is known. Okay. Now when upper specification limit type quality characteristic is considered, is it okay? So how do you compute ZU? Again the standard normal deviate, that is U minus x bar divided by sigma. So x bar is the sample average. What is U? U is the upper specification limit. And what is sigma? Sigma is the standard deviation, and the standard deviation is known. The area under the portion of the standard normal curve that falls ZL or ZU is the estimate of proportion non-conforming. I presume that you know the procedures when you start the reading the values from the standard normal table. So you will find the procedures, or this is the way to get these values very easily. So here I have explained the area under the portion of the standard normal curve that falls outside ZL or ZU is the estimate of proportion non-conforming, because here you are indexing your plan with respect to the proportion non-conforming. So how do you define the good quality when the proportion non-conforming is very, very less? How do you define a bad quality when the proportion non-conforming is very high? Now it is observed that as the distance between L or U and x bar increases, that means U minus x bar, suppose this value increases, what do you find? That the value of ZU will be more, and if the value of ZU or ZL is more, the corresponding area under the portion of the standard normal curve that falls outside ZL or ZU also will be less. So that's why the proportion non-conforming decreases. I think that the logic is made very, very clear, that if the distance between L and x bar or between U and x bar increases, the proportion non-conforming decreases. Okay. Now with this basic understanding, then what we do, that means we refer to the methods for acceptance sampling when you come across, or when you are dealing with the variables data, and your objective is to the control proportion non-conforming. Is it okay? And obviously we will be referring to a particular quality characteristics. Just make a note that all these variable sampling plans you design, you use with respect to a particular quality characteristics. If the quality characteristic changes, obviously you have to design a different the sampling plan. Now in this context, when your objective is to control the proportion non-conforming, there may be two methods as suggested by the researchers and the practitioners in this field, and these two methods are known as form 1 method, or it is also referred to as the small k method, and the other method is the form 2 method, or it is also referred to as the capital M method. So in we will be explaining what is this k or what is this M. Is it okay? So these are the very standard notations you will find in any textbooks on quality. Now it is to be noted that these are not different from each other. That means it's not that with the form 1 you get one sorts of result, and the form 2 you get another sorts of results, and then you have to make a choice. Is it okay? It's not like this. What do you try to do? That means first you apply the form 1 method and you take a decision. Now at the second stage you can modify the form 1 method with the form 2 method, and you apply the form 2 method, and again you take a decision. And as you are referring to the same case, is it okay? So obviously your decision must be same. Okay. So if you follow the rules or follow the methods properly, you will find that whatever decisions you have taken under form 1, same decision you will be taking under form 2 also. You are getting my point? So many times what you can do, that means the form 2 method you can use for verification purpose. Is it okay? So this is the point to be noted. So it is to be noted that these are not different from each other, rather one is linked to the other. Is it okay? So you don't start with the form 2, you start with form 1 and then you move to form 2. So okay. So while you explain the methods in details, you will understand these steps. So in a given situation, both the methods may be used, but decision regarding lot acceptance or lot rejection should be the same. So how do you use the form 1 method? First, ZL or ZU is computed with respect to a sample drawn from the lot. How do you do it? That means as soon as you compute ZL, that means it is a single specification limit case, and more specifically it is a lower specification limit case, whereas if you compute ZU, that means it is an upper specification limit case. So now you compute ZL and ZU, the formulas are known to you. Next, compare ZL or ZU with a critical value k. Is it okay? Now what will be the mathematical expressions for k, or how do you derive the expression for k? We are going to explain, we are going to discuss it very soon. The critical value is known. That means while you have designed a sampling plan, ultimately you need to know what is the sample size and what is the value of k. So these are the two parameter values in form 1 method. So what do you do first? With the x bar, with the L, with the sigma, you calculate ZL or ZU. Is it okay? So while you compute ZU, that means you must know what is the value of U. So either ZL or ZU compute, and you check whether ZL or ZU is greater than or equals to small k. So if this condition holds, then the lot is accepted, otherwise the lot is rejected. Okay, so this is a very simple procedure. You need to know the value of k by using its derived expressions. This point I have already mentioned. Under form 2 method, what do you do? In this method, we proceed to the next step to compute the normal variate value against L or U in an unbiased manner. Now what you might have noticed that when we compute ZL or ZU, it may be a biased estimate. Is it okay? This concept of bias can be explained from different perspectives, but just make a note that when you use say ZL or ZU, it may be a biased estimate. So if you want to avoid this bias and you want to recommend an unbiased estimate for ZL or ZU, what you against L or U, what you need to do? You need to compute QL or QU as the case may be, and this QL you compute by the modifying the value of ZL. That means you use this multiplying factor, that is root over n upon n minus 1, okay, for both the cases. That means ZL and ZU is already computed, and then you compute QL or QU. That means this is a normal variate you calculate, but this normal variate is considered to be unbiased and with the minimum variance. So the QL is equals to ZL into root over n upon n minus 1, and similarly QU is ZU into root over n upon n minus 1. Now these estimates are considered unbiased with minimum variance. N is the sample size. Is okay. Okay. Now, so QL or QU you compute. Next, what you do? An estimate of proportion non-conforming P hat is obtained by finding the area on the normal curve that falls outside QL or QU. Is it okay? So again you refer to the standard normal table, because the normality assumption holds. So you refer to the standard normal table and you just get the area under the normal curve outside, that is falling outside QL or QU, and this proportion this area is referred to as proportion non-conforming, and the notation is P hat. Is it okay? So the P hat, you get these values from the table. Now compare P hat with a maximum allowable proportion non-conforming denoted by M. So now we have defined what is capital M. So what is capital M? Capital M is maximum allowable proportion non-conforming. Is it okay? So how do you get this value? Obviously I will explain the procedure. Okay. So when you take up an example, we'll apply that procedure also. So if you find that this proportion non-conforming, that is the actual proportion non-conforming, is greater than the maximum allowable proportion non-conforming, so this is not a desirable situation. Obviously the lot is rejected, otherwise the lot is accepted. Okay, so the decision rule is known to you. You need to know the value of M by using its derived expressions like you do for the small k. Okay, so So now you have understood what is the form 1 method as well as the form 2 method. So form 1 method is also referred as the K method, and the form 2 method is also known as capital M method. Now what you need to do, that means you have to design the sampling plan. That means you must be able to derive the expressions for the sample size as well as the other the parameter values of a given the variable sampling plan, where the objective is to control the proportion non-conforming. So essentially it is an exercise for determination of N, K and M. So the following criteria are to be stipulated, like we do for designing any other types of sampling plans. Proportion of non-conforming indicating good quality P1. So this you must be able to specify, whether it is 1% or 0.5% or 0.05%. So that is considered to be good quality in terms of proportion non-conforming, for which the producer's risk is alpha. So if the value of P1 is very less, what you will find that the producer's risk alpha also will be very less. So maybe 0.01 or maybe 0.001, whereas if it is 0.02, that means this value could be just 5% or 0.04 or 0.05. And proportion non-conforming indicating bad quality. That means if the proportion non-conforming increases, obviously it is indicative of bad quality. So that value you must be able to specify, like say I say that 0.04 or 0.05 or 0.06. That means 6% is considered to be very bad quality, 6% proportion, say percent non-conforming, 6% non-conforming, for which the consumer risk is beta. That means even if the quality is extremely poor or very poor, you might say that this is there is a high probability of acceptance. So that is it is avoidable. Whether it is avoidable or not, that is a different issue, but right now this has been the case. You cannot avoid it. So it may be 10%, as high as 10%. Assuming normal distribution for X and the lower specification limit L, process mean mu1 for proportion non-conforming P1 and process mean mu2 for proportion non-conforming P2. Now this are determined. That means this process means mu1 against P1 and process means mu2 against P2. Suppose these are determined or these are known, then what you do, you refer to the following figure. So here what you are trying to do, that means you are getting the distribution of X. This is the distribution of X. So what you have over here, when the distribution is here, that means with the standard deviation of sigma, this is the process standard deviation, that is sigma. So this what is happening, so this is when the proportion non-conforming, suppose this is a lower specification limit case. So the value, that means this area, it's beyond L, that means this is the proportion non-conforming. So against the proportion non-conforming P1, already we have specified what is the corresponding value of mean, that is mu1. Now there is a shifting in the process, okay. So now mu1 has become mu2, or in other words P1 has become P2. So if P1 becomes P2, that means from the good quality to bad quality. So what is the corresponding value of mu2? So that also you can notice. That means that this entire area is considered to be the proportion non-conforming. That means it may be 0.01, now it has become 0.08 or 0.10. Is it clear? So this is so you must be referring to the distribution of X, right, when the sigma is known. So now corresponding to mu1, you calculate Z1, the standard normal deviate, and corresponding to mu2, okay, you calculate the standard normal deviate Z2. So what is Z1? Z1 is, that means you take the difference of mu1 from L, and this difference is expressed in standard deviation units. So, what is the standard deviation? That is sigma. And similarly, you compute Z2 mu2 minus L by sigma. Given sigma, we can determine the locations of mu1 and mu2. Is it okay? So, always you can do. Then what you do? Now you consider the distribution of x bar as shown in the following figure. So, what do you try to do now? So, you have this parameter, that is small k. Is it okay? Now, against mu1 you have the distribution of x bar. Obviously, the standard deviation is sigma upon root n as per the central limit theorem for both the cases. So, against mu1 you have, even if the quality is extremely the good, is it okay? What do you find? That when k is the parameter, that means this is the area, okay, that is beyond k. So, obviously, this is the the probability of non-acceptance, even the quality is very high. So, this is basically called the producer's risk. Whereas, when the quality deteriorates to mu2, what do you find? That you have with respect to this k, now this is the area under the curve which is within k, that means this value is greater than k. So, obviously, there is a possibility of its acceptance even if the quality deteriorates. Is it clear? So, we are considering the distribution of x bar. Now, what you do? You have under form 1, the lot is accepted if x bar minus L divided by sigma is greater than equals to k, and with these what you can say, like with these manipulations, what you can do, x bar minus mu by sigma upon root n is greater than equals to k minus mu minus L by sigma into root over n. So, this is the generalized expressions. Now, we have two expressions, like this means that the probability that x bar minus mu by sigma upon root n greater than equals to k times mu1 minus L, that means one particular value of mu is mu1, L is fixed, is it okay? That is the lower specification limit case, and sigma is the process standard deviation, and root over n. So, the probability is this, that means here mu1 minus L by sigma already we have computed, that is Z1, is it okay? The standard normal deviate, and so ultimately this becomes the probability that x bar minus mu by sigma upon root n is greater than or equals to k minus Z1 into root over n. This must be 1 minus alpha, that means this is the probability of acceptance, that is 1 minus alpha. What is alpha? Alpha is the producer's risk. So, in a similar fashion, when mu changes to mu2, you get these expressions, these probability expressions you get, that is the probability that x bar minus mu by sigma upon root n greater than or equals to k minus Z2 into root over n, that is equals to beta. What is beta? That is the consumer risk. Okay. So, hence k minus Z1 root over n is equals to Z1 minus alpha equals to minus Z alpha. Alpha is less than equals to 0.5 in almost all cases, and k minus Z2 into root over n is equals to Z beta. So, you have the two equations and you have two unknowns, and these two are independent equations, simultaneous equations you have. Now, setting these two equations simultaneously, okay, solving these two equations simultaneously, we get n equals to Z alpha plus Z beta by Z1 minus Z2 square, and k equals to Z1 minus Z alpha divided by root over n, Z1 minus Z alpha by root over n, and another expressions of k you get, that is Z2 plus Z beta by root over n. So, now what do? You follow the decision rule. When k is known, obviously you can follow the decision rule. So, what do you do? That means Z alpha, Z beta, Z1, Z2 you compute, you get the expressions for n. So, sample size is known. Next, what do? Either you use these expressions or these expressions. Now this expression when you use, that means you try to meet the alpha conditions, but you don't bothering about meeting the beta conditions. Whereas if you use this alternative expression, okay, for computing k, for determining the value of k, obviously you are trying to meet the beta conditions, but you are not bothering about the alpha conditions. Okay, so now you know the decision rule. So under form 2 we need to estimate the value of m. So the we know the expressions for k. Now if you opt for form 2, obviously you must have an estimate for the value of n. An estimate of m is the area under the normal curve, okay, beyond k into root over n upon n minus 1. Is it okay? So n is known, so obviously these expressions also will be known. Once m is known, follow the decision rule. Is it okay? So already we have given under form 2 what is the decision rule. For a given problem, both the methods may be used. Form 2 may be used for verification purpose. This point already I have explained. However, the decision regarding lot acceptance or lot rejection must be same in both the methods. Now here is an example. I will just go through it. In the manufacture of heavy duty utility bags for household use, the lower specification limit for the carrying load is 100 kg. So it is a lower specification limit case. We want to accept lots that are 2% non-conforming with a probability of 0.92. For lots that are 12% non-conforming, it's a very bad quality, okay, lot, the desired probability of acceptance is still 0.10. So this is basically the consumer's risk. The standard deviation of the carrying load is known to be 8 kg. That means this is the standard deviation known case. For a variable sampling plan, find a variable sampling plan and explain its operation. So here we have L equals to 100, P1 is equals to 0.02, alpha is 0.08, P2 is 0.12, it's a bad quality, 12% non-conforming. Still the value of beta is very high, that is the consumer risk is 10% and sigma is 8. So from the standard normal distribution table we get Z1, okay, against P1, that is 2.055, Z2 against P2, that is 1.175, Z alpha against alpha equal 0.08, you get a value of 1.405, and Z beta against a value of beta, okay, the tail area, that is 1.282. That means you are always referring to the standard normal the table. The sample size is, you use that formula and you get a value of n, that is 9.323, and you just make it the next higher integer, that is 10. And if you want to satisfy the value of alpha equal to 0.80, there are two the formulas for k. So if you use the first formula, that means if you want to meet the condition of alpha exactly, then the value of k is this 1.611, and if you want to, obviously you can refer to the other formula for k if you want to meet the the consumer's the risk condition exactly. Or what you can do, you can calculate the values of k using both the equations. That means there will be two values, and you may also take the average. Is it okay? So that is the third option you can also adopt. So we select a sample of 10 bags and find the sample average of the carrying load to be 110 kg. We can use either form 1 or form 2. Using form 1, we can calculate ZL as this 1.25. Since ZL is less than equals to k, the decision based on form 1 is to reject the lot. And similarly, you calculate QL. Is it okay? You are moving to form 2, so you calculate 1.32, and the corresponding the proportion that falls outside the standard normal value, that is 0.0934, and then you calculate m, that is the proportion non-conforming m. First you calculate the value of k into root over n into n by n minus 1, that is this value, that is 1.70, and you refer to the standard normal the table, and against this value of 1.70 you get area of 0.0446. That means 4.46 is the maximum allowable proportion non-conforming. What you are getting, that is obviously you are getting a value of say 9.34%. So since p hat is greater than m, the decision is to reject the lot. Is it okay? So for selection of variable sampling plans, standardized sampling plans you may use, like you do for attribute sampling plans, and the standards are, as I have already pointed out, MIL STD 414, and equivalent standard is ANSI ASQC Z 1.9 and Z 1.9, and equivalent ISO standard is ISO 3951. So we have completed our the lectures on the different types of variable sampling plans. In the subsequent lecture sessions we will be referring to a set of the numerical problems.